welcome to our first joint webinar with the FAIRSPACE and the ORCA Hub. My name is Lindsay Wilson. I'm the Hub Manager for the ORCA Hub. And today I'm joined by my colleagues, Anna Kedzier, who's doing all the behind the scenes work, and David Wearable, our Business Development Executive as well. And I see we're also joined by our equivalents from FAIRSPACE with Caroline and Emma on the call as well. So please do use the chat window. We're all here and we'll tell you more about the hubs and put in our websites as well so you can find out information. Today's focus is on teleoperation and telemanipulation. We've got 4 speakers for you from the 2 hubs. So we'll start with Alex, Dr. Zhibin Li, and Ziwei from FAIRSPACE, who are going to talk about bimanual manipulation. And then we'll move on to Katrin Lohan from ORCA, who's going to talk about, and I should say her talk has, the title has changed slightly. So her talk title is now Adaptive Interfaces for Remote Human-Robot Interaction Using Cognitive Load. And then finally, we have Suphi from ORCA, who's going to talk about autonomous control aspects for teleoperated underwater robot missions. So as I said, I would encourage you to use the chat window, ask us questions, ask the speaker questions, and we'll have time at the end of each of the talks for those. So without further ado, I'll stop sharing my screen and I shall hand over to Ziwei and Alex to get us started. So thank you everybody for joining us today. And just finally to let you know it's being recorded and we will put it on social media channels afterwards. Thank you.
All right, Lindsay, thank you very much for the invitation. I'm very happy to represent the FAIRSPACE and happy to share the high-level concepts that we have done in terms of pushing the boundaries over towards the futuristic research in the future space sector. So I hope everyone can see the shared screen well. So first half, we would like to chat about what are the new cutting-edge technologies we have developed in terms of both autonomous and teleoperated and shared control for bimanual manipulation in the space sector. And then most importantly, in terms of shared control, we are happy to share about new biomonitoring methods in order to monitor the mental load, and more importantly, how to quantify and evaluate the human performance in order to switch and coordinate between the autonomous and autonomous and the teleoperation mode according to the mental load. All right, so I will briefly go over to the high-level motivation, and we'll focus on the technical innovation here in the hub. And in the end, I would like to shed some light for the future vision and the future directions. So there's a strong industry need and interest for in-orbit satellite servicing, for example, for the maintenance and etc., where autonomous manipulation is very important for refeeding, maintenance, and etc. Right? So for all these complicated services, to automate that will greatly improve the efficiency and the mission, reduce the mission time. And also for space debris removal, as we have more satellites into space, there are a lot of this sector is growing there. And also more importantly, to travel further inside or even beyond the solar system, we need to assemble large structures in orbit, and not to mention a large future vision of base construction in the extraterrestrial surfaces, right? So as we illustrate here. So there are a lot of applications in future space sector that demands autonomy, as we discussed before, that where humans only need to provide high-level supervision and dedicate all these low-level tasks to the robots to automated procedures. And for complex situations where the situational awareness is important, this is the bit that human comes in, right? And also particularly when it comes to very complex operations, right? And to use simple manipulators and arms are not sufficient anymore, and therefore we need to have a bimanual manipulation similar to humans, or even multi-arm manipulation, to really improve the capabilities. Right. So these are the high-level motivations I have just covered. And as we briefly mentioned before, we have autonomous solutions, and we also develop online teleoperation with the delay to counterbalance the delay, and also have the dual arm operation for large structures and etc. So so here is a brief comparison and mention about the state of the art and how we are being different, and this are how the following technical developments really push the boundary beyond that. So Dr. Ziwei Wang will give a brief overview of this. Ziwei.
Yeah, thanks for the detailed introduction by Alex. And there are some related projects which have done by DLR and ESA and NASA for the teleoperation tasks. And in these projects, the counter project, which is done by DLR and the Russian Space Agency, is about the one dimension bilateral teleoperation task from the ISS to the Earth, and they use the optimized S-band link to reduce the time delay between the space and ISS communication. So that's so that could be a milestone for the communication channel. And later the metro tasks done by DLR and ESA, and the metro analog one done by ESA focus on the teleoperation for the planetary surface and the mobile rover from the ISS to the Earth. So they all consider the bilateral teleoperation with the haptic devices to provide a more accurate synchronization and haptic feedback.
All right,
so,
thank you for
so
Alex. Yeah, thank you for the nice introduction. So in short, in terms of big directions, you can see that there are preliminary works, many of them focus on the pre-programmed manipulation tasks, and the teleoperation control was one-to-one human teleoperation control, which is in the context of very little or limited delay. So in the next slide, we will show that how we can push the boundary further. So first, a quick overview of our setup. We have bimanual setup here, and with 2 robotic arms and 2 dual haptic interface here to teleoperate robot. And here is the setup Imperial side for human mental load, cognitive load monitoring here. As you can see, human sitting in front of this multi-model interface, right? So there's EEG and eye tracker, etc., to monitor the human load. So specifically to design the missions that are similar, those missions which are similar to the space construction and assembly of large structures, as we mentioned before. Here's the setup we use. We applied the industry connectors and have modular design like this to resemble the space debris removal in terms of capturing the object, and also the space assembly in terms of docking, connecting different standard modules, right? So this is how they're connected. So we'll show you later how this can be done autonomously. And so we have developed all this complicated software infrastructure under the FAIRSPACE project. So as you can see, it's fairly complicated module sitting behind all this. So this is the software structure sitting behind all these capabilities we'll show you. Skip these details for now, but rather look at this, the high level part that, so here on the right side, this is the human operation side or control station, where you have different visual cues, multi-modal interface, haptic device, and etc. And meanwhile, everything has been monitored, right? So the this whole system is automatically sitting at the background monitoring the mental load. And in the remote side, there are 2 components. So on the right, that is the remote side local control. So the local control has 2 parts. One is variable impedance control with adaptations, right? So any mistakes or human errors will be naturally corrected here to ensure it's safe to operate in space. And so another autonomous mode will naturally take over, right? So when the human mental load increases, or when the communication delay increases. So when there's too much latency, loss of package, and etc., when the communication is compromised, and then we would automatically switch to autonomous mode. So this dual mode operation ensures the resilience of the tasks. So here is just a simple demo to show, right? So the operator can give arbitrary command, but the robot will do exactly and precisely the safe motions as much as possible. So nothing is violated. All the physical constraints are compliant here to ensure the safety and feasible operations. So this is very good to prevent any human mistakes. So given this whole structure, we are able to collect a lot of operation data. So teleoperation, when teleoperation is running in the normal mode, we are able to collect a lot of data and establish database here. And so as you can see, so we can perform this kind of grasping tasks, for example, grasping and manipulation tasks using the dual arm. And we are going to do a lot of demos, for example, and not just the grasping, but also the docking, right? So for example, here you can see the docking task. So this is demo, right? So similarly, we can perform a lot of demos, and I will move to the next. So you can see there, this is the autonomous mode. So what happens here is that we have human bimanual operations that based on all the data, we can learn autonomously the docking. So as you can see here, is quite reliable. And also the same technology can be used for object capturing. So this resembles the space debris removal. So everything is done autonomously, right? So far things are done in a blind manner. So here I'm going to show you how we can integrate visual feedback. So this is purely autonomous using visual feedback here. So the robot has external camera that sees the object, and the auto capturing part is done autonomously. And as we said before, we have the control software and the whole infrastructure sitting behind it, naturally coordinates between the autonomous mode and teleoperation mode. So as you can see, the capturing is autonomous because it's a routine, repetitive tasks. So it's purely autonomous. You can see here, it's very smooth, repetitive motion as you see before, right? How it captured the first object. And then once it's captured, it is switched back to the human operator takes over, it switches back to the teleoperation, because the assembly and etc. requires a lot of contextual understanding. What if the object moves, for example, and this is teleoperated. So you can see here, you don't even feel the glitches when it switches. So the software takes care of the switch. And also thanks to the control, local control that guarantees the stability and the smoothness of the coordination between multiple modes. So the next, we will talk a little bit more about how the human monitoring is done during this teleoperation mode and shared control between the autonomous mode and the teleoperation mode. So we'll hand it over to Dr. Ziwei Wang.
Okay, thanks.
Yeah.
Thanks, Alex. Thanks, Alex. And according to what Alex introduced before, we can see a lot of bimanual teleoperation tasks are done by human operator, but that may be an issue if the human operators makes mistakes. From our knowledge, we can imagine that the human operator maybe get tired because of a lot of workload. So that would be a problem if a human operator makes mistakes, or due to the subjective things, maybe the human is not the best choice for the teleoperation. So that would be a choice for us to think about the shared control. And there are two points for shared control. The first one is the shared control with temporal consistency. That means the two human operators are collaborating on the ISS, and they could share the same visual feedback. They can negotiate with each other, equipped with the eye tracker. So in this way, the human-human collaboration through the interaction force, we can also call it haptic communication, could be a chance for improving the share control performance. And the next one, when they human operators will have the different comments, that means the physiological and motion information could be fused in case of the conflicting comments. So that so in this way, the arbitration between each other can be done that will allow for the equal rights negotiation. So next, Alex. So the previous one is we consider the two operators work in the same space, but in the common sense, the human operator on the ground could be supported by a lot of calculation capability. And as well as the human operator on the ground, the astronauts and the ISS could also provide full visual feedback and have a close access to the teleoperation scenario. So there would be another issue for the shared control with temporal inconsistency. So inferring the human intention for the astronauts on the ISS is the first thing to be done. And the next one, because of the two operators are located in different places, so the latency between each other should be considered. And the latency compensator under the remote communication will be used in the shared control with temporal inconsistency. And what's more, the remote intervention based on the operation performance is another problem for the two collaboration, because we cannot define which is the best master side and which is the slave side. So maybe we just need to define their rules based on their performance to distribute their follower or the leadership. So next. Yeah, we would like to realize the share control, but the first thing to be considered is the visual feedback interface. So you can see from the left figures, we use the fixed camera views that could be done to augment the visual, the interactive interface, which shows a visualization of the robot's state that based on the built-in joint angle and the torque sensors. So this interactive view can be further enhanced with the representation of the test states through the use of fiducial markers placed on the target objects. So this offer pose estimation that can be visualized in the interface. So the next one. The next one, we consider the human operator on the ground. So we would like to use this operator command interface consisting of the two Sigma 7 devices with the support of Microsoft HoloLens. So the Microsoft HoloLens is used to provide the gaze information which facilitates the human mental load estimation. So this mental load estimation is carried out in this early stage testbed that uses the eye tracking data provided by HoloLens 2, and the gaze focus on features such as the second frequency, fixation duration, blink frequency, and blink duration have been shown to be connected with the mental load. So in this way, the human mental load can be in the system. And the current system favors monitoring the mental load using the eye gaze from the head-mounted displays for the ease of acquiring the signals. So the eye-related features are just one of the many signals that can be used for mental load estimation. So the next one, we not only based on the gaze tracking, we consider a more physiological signals to be connected with the mental load estimation. So we developed a new wearable sensing platform, which consists of a 32-channel EEG cap, purple lab eye tracker, and a flexible wearable sensor that can capture the physiological signals like ECG, GSR, and body temperature, heart rate. So all sensors are synchronized by using the live stream layer. So the next one, based on the developed wearable workload sensing platform, we can carry out the teleoperation training experiments. Our training simulator is built on Unity. The current version simulates a similar task. So you can see from the left figures, we use the user interface to modulate the operator task. The operator needs to grasp the research module, moves towards the docking point, and avoids the obstacles. They need to dock the module onto the ISS. So we designed a reasonable scoring protocol to calculate the human performance based on their collisions, the time cost, grasp precision, and docking precision. So in this way, we consider the work modulation via confounding factors. So based on the latency, the time pressure, and debris obstacles, we can calculate the human performance based on the physiological signals. So this is a result of the mental load estimation based on the EEG signal. So we can see the theta, alpha, and beta bands in the range of 4 to 30 Hz. So these signals are related to attention, fatigue, and coordination parts of the teleoperation tasks. So we can see from the figures that the workload with latency will increase the collisions. So that will be an issue for the actual teleoperation. So the next observation is the workload with time pressure could increase the efficiency. So the issue that the latency will definitely increase the human mental load, as well as reducing the operation performance should be considered in the control design for the teleoperation. Yeah, so as I said before, the latency should be considered in the control design. So we like to know to which degree the delay will influence the haptic communication. So we need to answer the following two questions. The first one, how do humans react to delay during the haptic communication? And the next one, how does this affect the performance and the perception? So the previous human-human interaction in our work is changed into human-robot interaction. So we introduce a robot partner to provide the collaboration with the human operator. And we also consider the different time latency from the 0 to 540 milliseconds. And we compare the human performance and the time delay with the solo operation. So the next one, yeah, we can see from the results, the figure A shows the time delay versus the RMSE. So we can see from figure A, the accuracy between 0 to 60 milliseconds are not changing so largely. So we can see the accuracy of the 20 to 60 milliseconds delay levels are similar to those in the zero delay condition. And we can see from the figure B that shows the time delay versus the SPIRC, which is the indicator to show the smoothness. And this result can be also proved in the smoothness experiment. And even at high delay levels, the performance has not influenced so much compared to the solo condition. But we can see from the two figures, when the time delay increases and the subjects will recognize even in the small delay, and they adjust their motor behavior to compensate for the latency. So the next one, so after the experimental block, we asked a number of questions to the subjects based on the NASA questionnaire regarding the subject's perception of the interaction. So we can see the subjects could recognize a change in the interaction when the time delay is over 20 milliseconds, and they can receive this effect as the delay effect. So this change is also associated with the resistance and the noise. So based on the previous works, together with Edinburgh, we can develop the share control or solo or totally autonomous control mode for the teleoperation tasks, and the variable autonomy manipulate for the short range services in the space is a promising tool to address the teleoperation issues, and translate innovation research into impactful techniques with high TRL for the UK space industry is a very important for the current stage, and the social impacts which will benefit for the use in any remote or physical distance settings will be also used in the current stage. So that's all for our presentation.
Yeah, thank you. So another recap is that, as you can see, that there's a large range of work we have done together with Imperial and many other colleagues in the FAIRSPACE Hub. So as you can see here, a small summary of what we have covered today is that we have developed autonomous capturing, manipulation, assembly, docking, etc. And we also have teleoperation that it gives human the best experience and the minimum cognitive load to operate that. And to coordinate smoothly and seamlessly between the autonomous and teleoperation mode, we call it dual mode operation. And most important beyond that, as Dr. Ziwei Wang has just presented, right? So it's not just the operation between the human and robot, and the framework developed for the mental load monitoring and human-human interaction also allows multi-pilot cooperation. So it's not just one robot, one human operator, but multiple as a team, as a robot league that can perform all these complex tasks for the space assembly, debris removal, exchange of assemble large structures, exchange of different components for the maintenance in the space, and etc. And the same as what has been mentioned just now, right? This technology developed can be used not only for the UK space industry, right, to strengthen UK's international standing in the global landscape, but also a lot of these core technologies, the building blocks that can be used for infrastructure maintenance, for example, to improve our daily life. And especially in the post-pandemic time, there are a lot of this remote control technology can be super useful. Right. All right. So thank you very much for your time. That concludes our talk today. Thank you. Lindsay, hand it back to you.
Thanks, Alex. Thanks, Ziwei. I'm going to take over for the Q&A session. We're running a bit over time at the moment, so I think we'll just ask one question. So I don't know who wants to take this, but how could you apply the results of the mental load assessment to control the design for teleoperation?
Okay, so that should be my part, and with consideration of the mental load, there will be another level of the at the indicator besides the control performance. So in this way, we can consider a more sophisticated indicator, including the mental load, to estimate or to evaluate the human performance. So in this way, we can design a cost function, including the indicator from the mental load to play another kind of performance indicator, and to based on the mental load estimation, we can switch the role between the robot and human, or the different humans. And most importantly, we can use the mental load estimation to reduce the human fatigue. That will definitely increase the teleoperation performance. So that's my opinion. And other comments from Alex?
Yeah, I think you covered the most important bit. I have no further comments. Thank you.
Yes, thank you.
Any more questions?
I think given where we are with time, we'll maybe move on to our next speaker, if that's all right. So,
all right.
Alex,
thank you
very, very much for a really interesting presentation there.
You're welcome.
And
so
if I was to ask you to stop sharing screen and pass over to Katrin Lohan from Heriot-Watt University and part of the ORCA Hub. So she's going to be talking to us today about adaptive interfaces for remote human-robot interaction using cognitive load. So very much on the same theme, but this time looking at it more from the offshore perspective rather than the space perspective. So Katrin, if you're there, could you share your screen and start presenting, please?
Hi, everyone. So as David was already saying, I'm going to talk about adaptive interfaces for remote human-robot interaction using cognitive load. Given the talk we have heard before, I would say it's very close to what they describe as mental load, what we define as cognitive load here. Right. So in principle, coming from the ORCA Hub, I wanted to put this whole thing into perspective a little bit. So the vision of the ORCA Hub was to basically make it possible to get robots into the offshore environment and support the overall structures there, maintaining them, inspecting them, and so on, and having humans not in that dangerous environment anymore. So yeah, to just give you a bit of a background here, that's where I'm coming from. In principle, the ORCA Hub has four work packages, and we are here talking about the intelligent human-robot interaction, where we basically design, as similarly to the first talk, the interfaces, how we can use them in a more efficient way to control our robots. We started off and thought about how we can do this, and we basically said, yes, we want to have the human in the loop. That's why we are also using physiological data to track them. We want to have adaptive interfaces that are able to reduce the stress on the human, because beyond what our other colleagues were talking about, we are not only wanting to identify what are the problems, but we also want to give a more simplistic interface to the user so that they can still under pressure perform more efficiently. And yes, we also look into autonomous and semi-autonomous robots, but I'm not sure if I'm going to get to that part today. And of course, we also want to have industry involvement. Right, somehow, okay. so these are the interfaces we are talking about at the moment. So it's mostly control room environments that we are thinking of. So the example of the BBC's news picture on the bottom left is one of our environments we are targeting, but we do also have human-robot interaction in terms of real interaction, where maybe a teacher is then taking over. As to come back to the definition of what we defined as cognitive load, and I think our colleagues defined it more as mental load, we follow this idea of having three different aspects: the intrinsic load, the extrinsic load, and the Germany load, where all of them play a role in cognitive load to our perspective. And we want to adjust those. So what we did is very similar to our colleagues as well. So we measured all kinds of physiological data. In this case, we use the Tobii glasses, but we are also moving on to the HoloLens right now. We not only use eye gaze, but we use also the pupil diameter, which I'm not quite sure you can get from the HoloLens at the moment. So we are still trying to figure that out. We also use blinking rate, which has been shown to be very efficient to measure. We measure heart rate variability and heart rate. We also looked into gaze patterns and all of those. We then, after collecting a lot of data, we used machine learning to classify what cognitive load would be in there in our data. And in the end, we decided to classify it as three different levels of cognitive load, being low, medium, and high. And for more details, you can see on the bottom that we have some publications on that. We then moved on to, first of all, create a game, because it's just an easier environment where we put humans also in front of it, which is based, of course, on our requirements. So there, these little faces you can see on the screen. They are our robots, and I don't know if you can see it exactly, but there's also a little drone up here, where which is giving us the point of view in the end. And we designed this game so that we can use it with our learned cognitive load estimator, which gives us a prediction of what the cognitive load is for the user at a given time. And we adapt the interface based on that. So if the cognitive load value is high, we basically adjust the interface so it's easier for the people to solve the problem. So they have to go around and fix tiles or put out fires or I think to clean something and so on. All these details you can also see in our recent publication. But yeah, so in the end, we managed to do this, and we managed also to adapt this interface based on the cognitive load. Luckily, there was not so much delay here, because obviously we are not talking about far up in space control, but we are talking about one computer situation. Finally, we also moved on and looked also into how this affects the trust into our systems, because that was always one of our biggest questions. If the cognitive load is high and maybe also the latency is high, is the user still trusting the system? And we can see that there is a strong relation between the cognitive load and the trust, which we have seen in two studies. So basically we did one, which you see on the top right, where we interacted with different robots and they were helping the user to play a game, because the user was trying to find the pairs, and the robot knew where the relating object is. So they could ask or could not ask the robot. The robot was also able to cheat them, and we basically found that there's a correlation if they are stressed in that environment, and if they are not able to find the paired object, then they get more cognitively loaded, and then they also, if they get a wrong answer from the robot, they trust the robot less, of course. So which adds up to their cognitive load. And then we also are on having moved on to another so-called, let's say, game, but it's using our real digital twin from the ORCA hub here, where we use the forehead and also the Google speaker to see what kind of feedback would actually help the human in this environment more. I will just play this video so you get a little bit of an idea of what kind of tasks we ask our users to do here.
Hi, my name is Fred, and I'm your emergency assistant. Emergency alarm went off in North Tower Christmas trees. We have 4 minutes and 12 seconds to avoid evacuation. Okay. First, I'm activating emergency shutdown. Do you want to make a PA announcement to evacuate? So
as you have heard, like we are trying to put our users into a stressful environment where they have to avoid the evacuation of the base, and have actually a worrying situation. And as I was saying, we compared these two different.
Chapter 1 is available.
Good. Send it.
Sending the robot to the designated area. Quadcopter 1 is taking off. ETA to West Tower Christmas trees is 21 seconds.
And as you can already see from the human behavior, there's a big difference if you have a human-like interface like the forehead, or if you have just the speaker. She is in this case much more technically focused, and she's more onto the system itself when there is a speaker, rather than when there is a forehead. She's more socially engaged, which we might or might not want in this case. Okay. I will leave it with that. Do you just to give me a sec, I'm just swapping over this. I would like to thank all the people who were part of this, of course. And yeah, that's that. Are there any questions?
Thank you, Katrin. Really, really interesting. So I guess just a quick question from me before we move on, because I'm conscious of time. So how do you see this being useful for industry? Like, where do you see it being used by them?
Well, as we also saw in the previous talk, like measuring the stress or the cognitive load or the mental load of the human is really highly important nowadays, because we all, especially through the pandemic, changed into consumers on the back end of our computers, and we do most of our tasks through that. And as you might have also heard in the news, there's a big rise in stress and all those kind of things due to that. So I think that's one factor, but the other factor is also that industry is really interested in getting more safety into their environments. And when you focus on your humans, so if you measure them, understand what they think or what they are dealing with, you will really benefit from it. And I can clearly say that most industries are shifting towards that, and I really appreciate that, because I think it's a good movement from the industry side. Thanks.
Yeah, great, thank you. Okay, so we'll move on to our final presentation, and this is from Suphi Erden, another assistant professor at Heriot-Watt University with the ORCA Hub. And Suphi's going to talk to us today about autonomous control aspects for teleoperation underwater robot missions. So Suphi, if I could just ask you to share your screen, and then I'll hand over to you. Thank you very much.
So hi everyone, my name is Mustafa Suphi Erden, an associate professor at Heriot-Watt University. I'm also a member of ORCA project ORCA Hub, and I'm doing research in the field of underwater robotic manipulation in ORCA project. So today what I will be talking about will be some autonomous control or autonomous activity aspects that relate to teleoperation or telemanipulation of underwater vehicles. So what we envisage is something like this. You have an underwater vehicle in the sea or under any water with a manipulator, and we want to perform some task with the manipulator on the environment. This can be about inspection of some assets. It can be about cleaning of the surfaces of assets. It can be about taking some measurements. It can be about manipulation of things like turning on and off valves and so on. And we want this system to communicate to an operator with a teleoperation system. Like the person can hold such a possibly haptic device, which can also provide force feedback to the person. And there will be a monitor, and the person can see what the robot is seeing. And then the person will send commands to the robot to perform actions. So in this scenario, actually, the level of commands that can be communicated between the slave side, between the robot, and between the master side, the operator, shall be very high level commands. So we cannot manage, or we don't want to perform all low level tasks or low level control things that the robot will perform through this link. We don't want the operator to deal with that. For example, force control. If your manipulator will touch to the asset, you will probably need a force controller here. We don't want the operator to deal with this. We want an autonomous force controller mechanism on the robot. And stabilization of the position of the vehicle. We don't want the operator all the time to correct the position of the vehicle after deviations due to water currents, waves, disturbances, and such things. We want an onboard autonomous solution for this. So in such setup, actually, there are a number of low-level problems to be solved that need to be automated on the vehicle level, such as vehicle positioning due to reject the disturbances, a stable interaction with the physical structure, contact management. So if you want to do something on an asset, you will need a strategy to manage the contact, because it's very challenging in the presence of waves and a floating vehicle. Optimal base vehicle localization. So where will you put the base vehicle in an optimal way that the robot arm can perform in the best way? So these are the kind of questions we have been dealing with. And in my talk, I will show you what we have done regarding to these items. The first thing I want to show you is vehicle positioning under harsh waves. What you see here is our water tank experimental environment with a blue row underwater robot. And we are trying to control the position of this robot in the best way in the presence of waves. So what we have done, implemented, is a sliding mode controller, which you might be aware or you might have heard, but a sliding mode controller with a time delay term for the positioning. So time delay control is a rather new concept in the control theory. So in this study, we have transferred or translated or brought in the time delay control concept for controlling the underwater vehicle. So the main idea here is to make use of the history of signals, measurement and control signals in order to decide the control action. So with this time delay control embedded sliding mode controller, we could achieve very good results. What you see in these graphs is a comparison to a conventional PID controller on the blue row. So PID is a very standard, a very common industrial controller, and it is one of the most successful with such underwater systems. So we have compared to that. As you see in these graphs, the sliding mode controller performs much better in positioning the vehicle. And this better performance comes with more or less the same level or even less. Actually, it is less control effort, but in the same level control effort. So more or less the same level of control effort achieves a much better positioning in the harsh water environments, plus actually a time delay in the signals. We have introduced 100 millisecond time delay in signal communication as a disturbance. This is a disturbance. So time delay control is something different than the time delay disturbance. So in underwater systems, in teleoperated systems, time delay as a disturbance is a common thing that needs to be dealt with. So here we have that too, and we have dealt with that. So the next thing I want to show you is our dry robotic setup to emulate underwater interactions. So this is the system how we develop our underwater control techniques without the need of going under the water in a day-by-day basis. We develop things here and then we translate it to underwater and verify that. So this system is composed of a robot manipulator and a steward platform, and we can emulate the underwater vehicle movements with the steward platform, and we can control the robot arm under the movement of the base in order to perform actions on a structure. So what you see in this video is actually an experiment that we performed in real time. We had a vehicle in a water tank away from our dry lab. We had a communication between these two different places through internet, and in real time we got the movement of the robot platform, and we emulated this with our steward platform, and we could regenerate the vehicle movement in real time in our dry lab, and then experiment in real time again with our robot arm. Here you see the images or videos from the underwater vehicle. And the vehicle moves, our steward platform moves, and our robot performs action on the structure. So if you have such a system for manipulation on structures, you would like to control the location of your base, of your robot, in the best way that your robot arm attached to this base can perform optimally. So this requires to decide or to find out where is the optimal position for the base robot. The conventional approach in the literature is that people mostly find a optimal position, then the robot arm performs action, then the robot base switches to another position, and in that position again the arm does an action. So the robot base goes from point to point in a discrete way. So we wanted to avoid this. We wanted the robot base and the arm move continuously and simultaneously in a synergetic way. And we developed an optimal base location technique, taking into account what the robot arm needs to do, what kind of trajectory the robot arm needs to follow, and then the base is optimally located continuously, and the arm and base move together, and the arm can act on the structure. The same technique is extended for the case of maximal force transmission. Imagine if you want to turn a valve under the water, the valve might be very stiff. So then your robot arm might not be able to turn the valve in any arbitrary configuration. It should be configured in a way to transfer the maximum amount of power it can to the end effector. So for that purpose as well, you need to locate your base in the optimal way for maximal force transmission. This is what you see here is an experiment we performed with a pendulum, a very heavy pendulum, and with our optimal base location, we were able to dislocate or push this very heavy pendulum with minimal amount of joint torques, which means that we achieved maximal force transmission. So this is a video showing you how our optimal base location works synergetically with the robot arm manipulator. So the robot arm is performing a task on the structure, and the location is the base is localized and moved with the robot arm together in a synergetic way, and the arm performs action. I want to say that this action being performed on the pipe here is done without any vision, without any knowledge of the model of the pipe, or without any prior knowledge of the location of the pipe. The scan here, or drawing in this case, is performed only based on the force interaction. So the robot does not know in advance the surface structure or where the pipe is. The robot finds it, and just relying on the force interaction, it can follow the surface. And meanwhile, the base can act to make it most maneuverable for the robot arm. So in such a task, imagine that you have disturbances, you have a lot of external impacts that are moving the base, and from time to time, you will lose contact with the pipe because the base is floating. This is a very important and peculiar problem to underwater applications when the base is floating, actually, when the base is not fixed. So we developed a switching control algorithm to handle such situations, to deal with this, which means that when we establish contact with the pipe, we perform a controller, an admittance control, and when we lose the contact, we switch to a different type of controller, which will smoothly bring the arm back to the structure. And this switching controller proves to be very effective and very useful and important, to be honest, to maintain as continuous contact as possible. Besides that, due to the disturbances and due to different environmental structures, stiffness of the environment, the contact force changes a lot during operation. And for that, the controller, our studies showed that the controller needs an adaptation. When we applied admittance control, which means that a control based on the force sensing and a fixed control structure, our systems didn't perform very well, couldn't cope with the fast changing force levels. However, when we introduced an adaptation law, in other words, when we implemented an adaptive admittance controller, through these equations, the detail of which I will not go, but I just want to mention that there is such a parameter which is adapted, paying attention to the reference force and force error, and then our force control is regulated according to that and changed in time according to that, and adaptive control is implemented. So here what you see is the performance that we obtained with our switching and adaptive control strategy. In these pictures, you see a conventional controller performing on the pipe while the base is moving according to the realistic data of underwater vehicle under the water, and the arm is trying to inspect the pipe. As you see, there are a lot of gaps, which means that there was a lot of loss of contact. However, when we applied our switching and adaptive technique, these gaps almost all disappeared. And our measurements also revealed that. So this SDAAC thing, the last one in each group, is the controller, adaptive switching controller. We could eliminate this contact almost all in our sinusoidal base disturbances, artificial disturbances, and we could eliminate them very significantly in the case of realistic underwater vehicle motions. So these were the things that I wanted to share with you today. I thank you very much for your attention. If there are any questions, comments, I'm happy to answer.
Thank you very much, Suphi. Again, another very interesting presentation. So I realize that we've actually gone over time by quite a lot. So what I do is I'll just ask one question before we wrap up. Suphi, what are the challenges of telemanipulation in an underwater setting, do you think? What do you find?
So if I can go to my first slide, actually I can talk out of there. If you have such a telemanipulation system, the problems and techniques that I talked about are to enable or to enhance such teleoperation system by introducing or developing the autonomous control facilities on the vehicle. For telemanipulation, there are other issues, and the main and core issue is the communication of the command signals and the feedback signals in between the master and slave sides. So especially in underwater setting, you have a significant delay in transmission of these signals because we are under the sea If we cannot use electromagnetic waves, it is salty water mostly. So we need to rely on sound, ultrasound-based systems, which are slow and introduce time delay. So this delay of time is a major problem. Another thing is, under the water, the vision is very, it's not perfect. The vision is always blurred. And the videos you would receive on your monitor, the monitor of the operator, are always not very clear. So there need to be some intelligent things that recognize objects and that can make decisions given the blurred images and help and aid the operator. And a third thing I can add to all these is feedback, haptic feedback, not only visual, but haptic feedback. When the robot is touching to a structure, the operator will like to get a feeling of what kind of structure is this? Is it rusty? Is it soft? Is it already rotten? Is it something delicate? Is it very hard or is it flexible? So this kind of feedback is very useful for the operator to make decisions and also to operate in the best way. So this feedback provision is another challenge. So these three things are the challenges or the challenges of teleoperation, telecommunication aspect. And if we can introduce the low-level control and automation techniques in a good way, then our high-level system can focus on these teleoperation related aspects in a better way. Thanks.
Lovely. Thank you very much, Suphi. Well, I think as we have gone over our time quite a bit now, we'll wrap up there. So thank you once again to all our speakers, Suphi, Katrin, Ziwei, and Alex. And thank you to everyone who's attended this morning. Please look out for future webinars and future events that we put on. And we look forward to seeing you at our next event. Thank you very much, everybody, and have a great day.